There we go.
And do you want us to start with our videos off or on? How do you want to do that?
My preference is to keep videos on. I think it makes things a little bit more
Okay.
engaging as long as you're willing to be on camera.
Definitely, that's fine with me. Yeah, I was just wondering for like the very first part. I can just turn it on right now then.
Sure.
Okay, we're live streaming and you're back to being the host.
Great. So we are, looks like a little under 3 minutes from getting started. And for anyone joining us on the live stream, we're going to start in 1 minute. We're going to go ahead and admit folks from the waiting room. It'll take just a minute for everyone to get into the room here. And I think we're all here now. Thanks. My name is Nathaniel Jones, and I'd like to thank you for joining this webinar, URBANopt, an open source software development kit for community and urban district energy modeling by Ben Pauly, Rawad Al-Kantar, and Chris Mackey. This webinar is hosted by the IBIPSA USA Research Committee, with the goal to share new ideas from research to the building simulation community. Today's webinar is sponsored by Bauman Consulting. If you have questions during this webinar, please type them into the chat window. At the end of the 40-minute presentation, I will unmute you for discussion with Ben, Rawad, and Chris. AIA Continuing Education credit is available for attending this webinar. Please email info@aiaeb.org with your AIA membership number to receive credit for attending this event. And now I'd like to introduce Ben Pauly, Rawad Al-Kantar, and Chris Mackey.
Hi, everyone. My name is Ben Pauly. I'm a senior research engineer at the National Renewable Energy Laboratory in the Building Technologies and Science Center. NREL is a national laboratory of the U.S. Department of Energy. My work at NREL has focused on high-performance buildings, districts, communities, and campuses, and I help lead the URBANopt project. Rawad?
Hi, everyone. I'm Rawad Al-Kuntar. I'm a research engineer at the National Renewable Energy Laboratory. I'm an architect and a building scientist, and my research focus is on energy modeling at the building and urban scale. And I'm one of the lead developers of URBANopt. Chris?
Thanks, Rod. I'm Chris Mackey. I'm a co-founder of Ladybug Tools, and I am one of the lead developers of the interface for URBANopt that we have built with Ladybug Tools to export urban energy models from Rhino Grasshopper. So I think we can turn it over now to Ajit for a quick word from the sponsor.
Thanks, Chris. Yeah, hi, I'm Ajit Naik, Senior Energy and Commissioning Engineer with Bauman Consulting. We're sponsoring today's webinar. We're a building engineering consulting firm offering building simulation, commissioning, integrated energy master planning, and green building consulting services. We've got offices in Chicago, DC, and Frankfurt, and we work on projects throughout North America, the Caribbean, and Europe. While we've been working on innovative and high-performance buildings since our firm's inception, we've really built an increasing focus on high-performance communities over the last 10 years, ranging from university campus retrofits to new neighborhood developments to municipal scale energy master planning. Really, we know that high-performance buildings by themselves aren't enough. The opportunities provided by sharing resources and reducing waste in communities are essential to achieving the sustainability and resiliency goals that our communities are increasingly adapting. But these goals aren't enough. We need the tools. That's why we really jumped at the opportunity to sponsor this webinar. The stuff that Ben, Rawad, and Chris are developing in URBANopt and associated tools are really amazing and critical for realizing these efficient communities. And I'm personally super excited to hear what they have to say today. So thanks again for the opportunity, and take it away, fellas.
All right, well, thank you very much. And before we get started, we'd just like to really thank BIPSA and thank Bauman Consulting for sponsoring today's event. That we really look forward to presenting an update on our work and having a discussion at the end. So we're going to talk today about URBANopt, which is an open source software development kit for community and urban district energy modeling. And I'm going to start off today by talking about kind of the motivation around communities and districts and why we're interested in developing analytical capabilities for to support projects at this scale. And then I'm going to introduce URBANopt and then hand it off to Rawad, who is going to talk in more detail about the URBANopt capabilities and specifically focus in on some of the core URBANopt software development kit or SDK modules. Then Rawad will hand it off to Chris Mackey of Ladybug Tools, who's going to talk about some of the integrations that Ladybug Tools has been making with the URBANopt SDK. And then I'll wrap things up at the end by talking about some of the other modules that we're working on developing for URBANopt, including grid-interactive analysis modules and district thermal system modules. Next slide. So why are we focused on districts and communities? You know, there's been a lot of effort for many years to improve the efficiency and performance of individual buildings. We've made a lot of great progress in that area. More and more, it's becoming about scaling these solutions and also thinking about how buildings integrate into the larger energy system. And so communities or districts, when I say districts, I'm talking about a scale of tens to hundreds, maybe a few thousand buildings. When I'm talking, you know, tens to hundreds of acres of land area. This is really an ideal scale when we're looking at kind of accelerating sustainability, as EcoDistricts talks about, because you can innovate quickly, test out a variety of solutions, but also you're starting to reach, you know, a larger number of buildings and energy systems and can have more and more impact. So some specific reasons why we're interested in districts and communities. One is that it can allow us to engage earlier in the process. Say we're engaging with master planners in a new development or the redevelopment of you know, like a brownfield area. By thinking about energy efficiency and energy strategies earlier on, those kind of strategies can be incorporated into things like community design guidelines to influence the energy performance characteristics of building systems as they're being built later on. We can also achieve economies of scale. So we're talking about touching potentially tens of millions of square feet at a time, rather than individual buildings at a time. And then there are some unique opportunities within districts to actually achieve additional energy savings by taking a multi-building approach. So for example, if a district has a good mix of loads, good load diversity, maybe there are some buildings that are in a heating mode while other buildings are in cooling mode, there may be opportunities to take the waste heat from the buildings that are in cooling mode and utilize that through a district thermal system, for example, to heat other buildings or end uses that need heating at the same time, achieving more efficiency than you could achieve in an individual building by building approach. These are also great test beds for new technologies, utility programs, and business models. Next slide. So at NREL, we've actually been working, for the last 4 or 5 years, really focusing on these districts and communities in partnership with DOE and several district partners as a part of the Zero Energy District Accelerator, and also these national partners that are listed here. In this accelerator, we had 6 districts from across the US who are all working to achieve high levels of energy performance, whether it was zero energy or low carbon emissions across the district. And what we did as a part of this accelerator is we convened these leaders to go through an energy master planning process and really understand what were the key strategies that were working to develop these sort of integrated solutions to achieving high performance, and what were some of the key challenges that they face. Next slide. So today I wanted to highlight a new publication that just came out earlier this week that I think is relevant to kind of the motivation for developing these sort of district scale analytical capabilities. This is a guide to energy master planning for high performance districts, and we've actually encapsulated a lot of the strategies that were identified in the Zero Energy Districts Accelerator into this document. And relevant to today's discussion, throughout the document, we try to highlight some of the different sort of analytical approaches and types of analysis that are needed throughout the development of a high performance district and community. And so as a part of that, you can check out the guide and get more information kind of about the real world projects that are driving the needs for analysis in these areas. But as a part of that, one of the key things that kept coming up in our discussions with our partners was that, in these projects, they're trying to integrate a variety of energy systems, from buildings to distributed energy resources, to the grid, to electric vehicle charging, and then also understanding all of the potential impacts in terms of things like mobility, comfort, whether it's within buildings or outside within a community or district. And so the analytical needs were very dependent on the specific questions that were being asked, on the different mixes of technologies. And it really became clear, there was a need for more analytical capabilities in this space, and B, that it wasn't that a single tool could tackle all of the types of problems that were or questions that were being asked. And so, we saw things like, different groups trying to utilize Energy Plus and Open Studio, which are, very much focused on, enabling analysis in a kind of building by building approach, and then really trying to aggregate those results up, try to approximate interactions across buildings, and doing that a lot in kind of customized spreadsheets that they develop for specific projects. So if you go to the next slide, that's, by going and partnering with these districts and kind of seeing their pinch points and understanding their needs, we embarked on the development of URBANopt, which is a analytics platform for communities and urban districts. We started this effort about 5 years ago, kind of as a internally funded proof of concept at NREL, and then we kind of worked on building that out, building essentially a new layer of analytical capabilities on top of DOE's open source energy simulation engine and Energy Plus, and also on top of the Open Studio software development kit, SDK. And so we then transitioned from that to multiple DOE funded projects, and have been working with a variety of partners, including Lawrence Berkeley National Laboratory, several university partners, and some industry partners like Chris and Ladybug Tools to really build out this concept and capabilities. So a key thing, and this is shown in the graphic on the right, is that URBANopt is a modular open source platform. We're focused on that underlying analytical capability, the SDK, represented in the light blue. And so the SDK is really like a toolbox for commercial software developers. And so our target audience for URBANopt are commercial software developers like Chris and Ladybug Tools who want to utilize URBANopt capabilities. Maybe it's a particular part of URBANopt to utilize that in their end user facing tools, applications, interfaces, web services, etc. So the ultimate vision for URBANopt is that it will be supporting potentially a variety of commercial software developers for a variety of different use cases at this community or district scale, and then ultimately kind of scaling that up through influencing a variety of projects for a variety of clients. So with that, I'm going to hand it off to Rawad, who's going to kind of talk a little bit more at a high level about URBANopt, but then go into some of the details on the URBANopt SDK core modules and talk about kind of the modular open source development approach that we've taken. Rawad?
Yes, yeah, thank you, Ben. Next slide. So first I will talk about URBANopt functionality and a typical analysis workflow of URBANopt, and then I will describe more in details like the software architecture behind this platform. So for URBANopt functionality, first URBANopt SDK can organize geospatial information about the buildings and energy systems. And this is basically the location and the geometry of the buildings and the district systems. And also it enables the creation of highly customized analysis and automates, and with all these tools that we are integrating in URBANopt, it automates the generation of physics-based models for buildings and district systems. And also it manages the simulations and post-processing of the results. And most importantly, the SDK can manages the integrations with a variety of tools. Next slide. So now I will walk you through a typical URBANopt analysis workflow. So the first step of this workflow is gathering geometric information, which is like the building footprints or 3D models if we have these available, and combining this geometric information with non-geometric information such as the building type, the properties of the building envelope, or properties of the building systems, for example. And after combining this non-geometric and non-geometric information, then next URBANopt will automatically generate the baseline scenario, which is the business as usual model and designed to meet the code requirements, the minimum code requirements. And since URBANopt is based on the notion of scenarios, then users from this baseline model, they can start generating other scenarios such as the high efficiency scenario and the high efficiency plus PV scenario, for example. And then in the last step, URBANopt will run these scenarios and the simulations, and also post-process the results, and users finally can visualize the results across all of these scenarios. Next slide. So now we talked about, I gave you a general overview of the functionality and the workflow of URBANopt. Now I will talk more about the software architecture behind this platform. We discussed about that how we want to tackle the design of URBANopt, and that we expect multiple tools to work together to tackle a specific project and not just a single tool. So we designed URBANopt as a series of modules, as you can see here, and these modules can be assembled in a specific way in order to create a customized workflow for a specific project. So as you can see in this image, we have multiple modules that are assembled together, and each of these modules have its specific functionality. So for example, we have a module that takes care of creating the building geometry, defining the envelopes, or taking into account the auto zoning of the building and the shading surfaces from the surroundings. And another module can be focused on detailing HVAC systems, for example, and another module for modeling the PV systems and distributed resources. And the users can assemble these modules in a specific way to customize their own workflow for a project of their interest. And I would like to mention here that before this, I would like to mention here that that we designed this in a way that users can swap out a module with another module. So, for example, if the user decide to use a different engine to simulate the distributed resources or PV systems, then this is possible. That what you can see here, the REopt Lite API module can be swapped out with a different module. And with this said, URBANopt is modular, highly customizable, and multidisciplinary. Next slide. So when we are assembling all of these modules together, we had to come up with common definitions or terms that in order to make sense between these modules and to ensure consistency. So we came up with a set of definitions, and we think that these definitions can map to objects of most of the energy tools out there. So I will start with these. So first of all, we have a feature, and the feature is a single object in a district energy analysis, such as a building or a district system. Then we have a feature file, which is a group which include all the features and along with their details. And then we have a scenario, and the scenario is one potential realization of a feature file assigned with specific properties or energy-related properties. So, for example, you can have the same feature file and assign a set of simulation inputs to it, and the same file you can assign another set of simulation inputs, and these will be two different scenarios. And finally, we have a project. And the project is concerned with comparing different scenarios. So a project includes multiple scenarios, and users can compare the economics and energy implications across these scenarios. Next slide. So now we define these terms. URBANopt will support many types of feature files, because these feature files can come in different formats. And the first format here that we are supporting is the GeoJSON format. And this is a format, a standard format for pulling geographic information. So what we did is we took this GeoJSON file and we extended it a bit in order to include the specific attributes and features that we want. For example, like building attributes such as building type, floor area, footprint area. So after we extended this GeoJSON file, we constructed a GeoJSON Gem. So we constructed a GeoJSON Gem, and this GeoJSON Gem have the functionality to parse all the information in this feature file and translate it into OpenStudio energy models, as you can see here. So this GeoJSON Gem, which is a module, have methods that can first of all validate the feature file, just to ensure that all the required properties are there and that they are in the correct format. And it have a lot of other methods in order to parse this information and do this translation into energy models. Next slide. And we also designed URBANopt at the core to have a scenario mapper. And the main goal here is to assign a template or a package of simulation inputs to the features in our scenarios. So rather than doing this in a hard-coded way, what we did is we created a programming class called a mapper class, as you can see on the right. And this mapper class have methods that can apply simulation inputs to the features. So if you see on the right column, we constructed here like 3 different mapper classes. The first mapper class is the baseline mapper class, which include methods that assign baseline standards to the features. And then there's a high efficiency mapper, for example, that inherits from the baseline mapper, but also have OpenStudio measures that can improve the lighting loads, improve the equipment loads, and also, for example, add photovoltaics. And these mapper classes are then assigned to the features in our scenario via a scenario CSV. So as you can see on the bottom left, the baseline mapper is assigned to the first feature, which is a building, and the high efficiency mapper is assigned to the second building. And I would like to mention here that these mapper classes are highly customizable, and users can edit these, extend them, or even create new mapper classes with different measures that can be applied to the features. And this actually gives the users great control on how they want the features to map to simulation inputs. Next slide. Then there's a need for processing the result, post-processing the results. And this is not an easy or trivial task because, I mean, there's many types of aggregation methods that can be used, also different methods to summarize the results. So in order to do this, we developed a scenario post-processor, and this post-processor includes method that can aggregate the results in different ways and also summarize key metrics and results that are reported in terms of feature and scenario reports. So this post-processor will take in individual feature reports and aggregate them to create the scenario level results and reports, which can then be visualized. So in order to ensure that this post-processor work in an efficient way, we had to define a schema for our results. So we created a schema for the features and also the schema for the scenario level results. And this schema define all the results that the users want to output or visualize. So for example, if in the feature report, we have these different sections, which are like the results of construction cost results, program results, and reporting period, which is a section that have all the energy results for a specific period. And I want to mention that here that the users can modify the schema in order to include or exclude results as they wish. Next slide. Finally, URBANopt workflows are released via example projects. As you can see here, this is the first example project that we released, which only include the core gems, which are the GeoJSON and the scenario gem, but we developed new capabilities and other gems that are released in new example projects. And here on the bottom, there's a link to URBANopt documentation, and I encourage everyone to visit this link in order to learn more about the URBANopt platform. And also there's a guide that guide you through step-by-step how to run the example project and all the scenarios that we developed, and also how to customize these workflows and create other workflows of interest. I will now hand this to Chris to talk about the integration with Ladybug Tools.
All right, thank you, Rawad. Yeah, over the next 15 minutes, I'm going to give you a bit of a tour of the interface that we've built for URBANopt in Grasshopper, in Rhino Grasshopper. And just to give situate ourselves within the whole Ladybug Tools plugin suite right now, I'm just going to say everything I'm showing you is from the latest plugin that we just released 2 months ago. So it's officially released on Food for Rhino 2 months ago. So those of you familiar with the legacy plugin, this is a brand new replacement for that. And so I'd encourage you to go and install from Food for Rhino if you're interested in playing with the interface. And also everything I'm showing you is particularly integrated into this dragonfly insect. So some of you may be familiar with our ladybug and honeybee insects that are meant for climate visualization and modeling of individual buildings. But Dragonfly is specifically targeted and optimized for the urban scale modeling of URBANopt. And all of the integration and connection to URBANopt is through the Dragonfly insect. So with that sort of preamble, we've tried to optimize or at least give a range of workflows that users can take advantage of in order to construct urban scale models for URBANopt. And we tried to tailor these to the most common types of urban data sets. So I'm going to take you through each one of these to show you how they work from the Rhino Grasshopper interface. Starting first with the coarsest or most abstract way to assemble models from building footprints, and then moving to building solids, which I'm sure many of us are familiar with working with in early stages of design, working with building massing. And then finally, the most detailed way of constructing our urban scale models, which involves the ability to customize zones on a room by room basis. So first, to start off, before sort of diving into the building footprints workflow, I just want to say that all three of those workflows make use of these very important sort of template objects that we developed specifically for the new plugin and are pretty critical for enabling urban scale workflows. So the first of these kind of template objects is a program, or those of you who are more familiar with OpenStudio and OpenStudio SDK may know this as a space type. But essentially, we have objects that contain all of the loads and schedules that describe a particular space or a particular building or floor of a building. And you can create these objects from scratch using the components in the Grasshopper interface we've put together. But we also include an entire library of programs with the Dragonfly plugin that come from the Department of Energy commercial reference buildings and the OpenStudio Standards Gem. So we have templates that are pretty much ready to go for a range of different buildings, about I want to say between 15 and 20 different building types and several different room program types within those buildings. And we also have them organized by vintage or different versions of ASHRAE 90.1 so that you can basically set up your models starting from a template that corresponds to standards as opposed to having to assemble everything from scratch. And also very importantly for urban workflows are that these program types can be blended together based on ratios of floor areas, so that you can make aggregate programs that you can apply to entire stories of a building or even entire buildings themselves. So this is one key object. Another very important sort of template object that we've added to the Ladybug Tools plugin to enable urban scale workflows is the construction set. Again, those of you familiar with the OpenStudio SDK probably know of the default construction set that this object maps to, but it essentially contains constructions to describe what all the walls, the roofs, the floors, the windows, etc., all those different surface types of a building, what construction is assigned to them. And Dragonfly it ships with a version or with a library of standards of constructions that come from different versions of ASHRAE 90.1. So you can very easily apply construction sets that, well, I should say ASHRAE 90.1 and the climate zones that are associated with that. So you can apply these construction sets broadly to a set of buildings in an urban area and know that those constructions are compliant with a given version of ASHRAE or a vintage that's associated with those building types. So with that introduction, I'm just going to show you a quick video of the From Building Footprints workflow that utilizes these objects. So we have here a data set of a few hundred building footprints imported from a GeoJSON. Here you see I'm assigning different floor heights to those buildings and passing those footprints into a component that assigns all the properties needed for an energy simulation. Here I'm taking a program type of a mid-rise apartment and applying that to all the buildings. I'm taking a construction set for the climate zone that these buildings are in. And out of this, for every footprint, I get a separate building object. And each of these building objects can be translated to an OpenStudio model or its own honeybee model. But you can assign parameters for window ratio, was what I just did there. And then lastly, you combine these all together into one urban model and then export to get one Energy Plus model or OpenStudio model for every single building footprint. And here you can see what each of those Energy Plus models looks like. You can see that it only exports the surrounding buildings within a certain radius that's adjustable, so that you can easily parallelize these types of simulations. So that gives a bit of a sense of the From Building Footprints workflow. I'll just say quickly that we have a number of other features built into this workflow. We have straight skeleton methods for automatically generating core perimeter zones for any type of building footprint. whether that's concave or convex. And just to show you that that this can handle a variety of different types of shapes and building offsets, you see here an animation of just adjusting that perimeter depth for a given concave building. And you see that it's able to resolve the even as the perimeter depth comes into contact with the core zone, that's all smooth and works together. So the from building footprints is probably very useful for very early stages of design, or in cases where the only urban data set available is simply just footprints. But a lot of the once you get past those very early stages of design, chances are that you probably have massing, building massing that's associated with the given set of designs that you're exploring. So in order to do this, we have methods that allow you to create entire Dragonfly buildings from each individual solid, each closed solid within a Rhino grasshopper definition. And to give you a sense of what this is like, here I have a few closed volumes that represent some office buildings in the downtown area. So I connect those to a component that assigns all the properties that are needed to pass into an energy simulation. So here I'm specifying floor heights, where we have a first floor at 5 meters, the 2 stories above that at 4 meters, and everything else at 3 meters. And so that will be used to divvy up the building over the height of the building, split it up into floors. I'm connecting a blended program type you saw there in a construction set to apply all the properties to these buildings. And then out of this, I'm getting one building object or one model essentially per building solid. Then I can simply take those buildings, convert them, export them into the 3D format for energy simulation. And you see that the Dragonfly interface is smart enough. It has multipliers built into it. And also you can see it's only exporting, again, those buildings, those neighboring buildings that are within a certain shade distance radius from the other ones. So that gives a bit of a sense of how that workflow happens. Just to give you a sense of how it simulates. So once you combine all those buildings into a single Dragonfly model, that can be exported from this component to an URBANopt compatible GeoJSON file, which you see here. And that GeoJSON contains links to those individual honeybee models, which each individually get mapped to an OpenStudio Energy Plus model. And by simply connecting the GeoJSON to this component that executes the URBANopt CLI, you'll see it will start to run each of those buildings in parallel. You see the CPUs on that machine bumping up there. So that gives you a sense of just the general workflows for running simulations. And just to show you, this is what that GeoJSON for that particular from building solids example looks like. And again, each of those features is linked out to a different Energy Plus OpenStudio model. Once we've run that simulation, once we've executed that URBANopt simulation, we can load all the results back into Grasshopper. We have several result parsing components for various different types of visualizations. And just to show you a very common one, you can color all of the essentially the rooms or stories in this case of those urban buildings with their heating and cooling loads. And so at face value, this allows you to just understand which of the things are driving heating versus cooling over a district. We can see that, let's say, these residential buildings have a lot more heating demand than the commercial ones. And importantly, we can also scroll through the results on a finer time step basis. So for example, here's that exact district, but we're scrolling through the months of the simulation to see which months have the most overlap in heating and cooling loads. And we see some of those months there, like in May or October, I think, we had some buildings that were heating and others that were cooling dominated. So we can already start to see if there are opportunities for load sharing between a district system, between a lower temperature district system. And we can even scroll through this or aggregate all those results, those time series results, and look at the cooling load on an hour by hour basis, the heating load, and the overlap between those in the entirety of the urban district. And you can see, just to give an example of how the types of explorations we can do with just a mix of 50% residential and office. We don't necessarily have a very high overlap, but starting to mix in more diversity of programs, like let's say restaurants and a hospital, that overlap is able to boost up a lot, such that those spaces, particularly the restaurants that are still in cooling mode, the heat rejection of those can serve as a resource for the rest of the buildings in the district that have a higher heating demand. Okay, so briefly, I'm just going to go over the very last workflow that then the most detailed workflow that we put together for the Grasshopper plugin, and explain to you a little bit of how the kind of Dragonfly building schema is structured, and sort of what's been done to it in order to optimize it for the urban scale. So essentially, at its core, all Dragonfly objects are represented by 2D floor plates. So everything is assumed to be an extruded floor plate, which does present some limitations for certain building types, but that it allows us to dramatically reduce the size of the urban models. A typical Dragonfly model is, on average, you're finding about 1/10 the size of the full 3D representation, 1/10 of the file size. And it allows a lot more flexibility, let's say, to specify multipliers for an entire story to represent a story repeated over the height of the building. And so at its core, though, you can still specify individual rooms within a story, within a Dragonfly story. So you're able to build up on a room-by-room basis a Dragonfly model such that different programs are represented by separate zones in the ultimate OpenStudio Energy Plus models. You can join those into a story and then have different stories over a height of a building that you use to represent that final building. And this is the most detailed way of constructing models. So just to kind of talk about this very abstractly and diagrammatically, a Dragonfly model contains all of the buildings of a given district. You can have each of those buildings is constructed of stories, and those stories are constructed of 2D room floor plates. And of course, we also support context shading for objects like trees and other things that can block the sun to several buildings, but aren't themselves consuming energy. And just to give you a sense of what's really happening in the underlying part of the process when everything gets exported into that URBANopt compatible GeoJSON and the OpenStudio Energy Plus models. The thing is that everything is actually getting mapped into a honeybee format, which is a full 3D representation of the building geometry. But the coarsest object of honeybee is just the room. And so you can imagine if we were trying to make an urban scale model just from honeybee rooms, we'd have to work with arrays of arrays and lists of objects to represent that hierarchy of stories to buildings to a district. And so Dragonfly objects are essentially trying to make it much easier to work with this hierarchy on an urban scale. And so you see the finest object in the Dragonfly schema is that room. There's nothing smaller. There's no individual surfaces. And you have to translate the Dragonfly object into that honeybee format to get individual faces or windows. So again, this is a major reason why the file size and the Dragonfly models are so much smaller and flexible and easier to edit than their equivalent 3D counterpart. And it's also why we say it's optimized for the urban scale. So with that, I think I've kind of covered the three main workflows. I think I'm going to pass it back to Ben to close us out for this webinar. So thank you.
All right. Thank you, Chris. So Rawat and Chris really focused in on some of the core capabilities of URBANopt that we initially developed in the building's core modules. These are mainly focused on enabling, the analysis of energy efficient buildings across, collections of buildings in a community or a district. What I want to highlight in the last several slides here are some of the other modules that we've been working on developing. These are kind of ongoing efforts. In particular, the Grid-Interactivity modules and the district thermal system modules. So next slide. So for the Grid-Interactivity modules, this part of our project is focused on enabling analysis at a community scale where we can look at trade-offs between building efficiency, building demand flexibility. So buildings that are able to control sort of when they consume energy, maybe shift or shed load or modulate their loads over the course of the day, and investigate the trade-offs and synergies of those approaches and their impacts and interactions with distributed energy resources like batteries, whether they're behind the meter or community scale, and PV, whether it's rooftop or community solar or canopy solar that you might see in a district. And so the idea is that by being able to make integrations with modeling for these different technologies, that we can look at sort of the co-design of these different energy systems and come up with a more optimal overall solution. So we've actually made some initial integrations already. We've made integrations between the URBANopt SDK and the REopt Lite API, or Application Programming Interface. And REopt is a tool that's developed at NREL that takes in a load profile. So basically, it gets load profiles from URBANopt, either at an individual building level, which is shown in the bottom left figure, or in aggregate across a whole district. It takes in a load profile, and then it does a techno-economic optimization where it looks at the different ways that it can meet that load profile. So, for example, you could give it options of purchasing electricity from the utility, generating electricity on site with PV, storing or discharging electricity in batteries, and it finds the cost optimal from a life cycle cost perspective sizes of PV and batteries, and optimal dispatching of battery systems, given all of those economic considerations. So we're able to send these sort of jobs to the REopt Lite API and then get back results into URBANopt. We've also made some initial integrations between the URBANopt SDK and OpenDSS, which is a distribution system power flow modeling tool originally developed by EPRI, open source tool that allows modelers to look at sort of the performance of a electric distribution feeder. So what we've done is if a electric distribution feeder is specified within the URBANopt GeoJSON file, which is kind of visualized on the right there, and then connected to buildings, we've automated a lot of the workflows to basically take the building simulation results that come out of URBANopt and, utilizing a tool called Ditto, translate them into OpenDSS models so that you can then understand the potential impacts on the distribution system. So say there's a community with a high level of renewable energy integration. There might be some times where a lot of energy is being exported back to the grid. You could do things like look at how does that impact the voltages at different points in the grid, and do those voltages stay within the required limits, or are additional sort of controls needed to handle that. Next slide. So a lot of these grid interactive capabilities were originally kind of proved out as a concept in a project that we did near the Denver airport in the Peña Station Next. This is a 400-acre mixed-use development where we were working with Panasonic and Excel and the local developer, LC Full and Wider in the city of Denver. They were looking at different ways to achieve high levels of efficiency and renewable energy integration. Next slide. And so if you want to dive in a little more detail into kind of what this type of combined building and DER and grid modeling can look like, I'll just point to the paper that we reference here. Next slide. So as a kind of the other key set of modules that I wanted to highlight are the district thermal system modules. So this is where NREL is working closely with Lawrence Berkeley National Laboratory, the University of Colorado Boulder, also working with NG to understand kind of the different analytical needs around district thermal system modeling. And so this figure shows that there are several generations of district thermal systems that are either in existence or being built today, ranging from more traditional, less efficient systems with central generation to what we would consider sort of the fourth and fifth generation type systems, which are moving to more of that ambient or near ground temperature loop system, able to utilize lower quality sources of heat energy or sinks of energy, utilizing heat pumps, so potentially electrifying heating and cooling. And so the district thermal system team is working on developing a variety of component models, and they're leveraging the Modelica environment and approach, and particularly heavily leveraging the Modelica buildings library to develop out templates and component models to model these types of district thermal systems. And so if you go to the next slide, just to give you a sense of the kind of complexity of this type of modeling, and this is what really drove us from kind of taking a Energy Plus Open Studio based approach to more of a Modelica approach, which is better suited for modeling all of the controls in these district thermal systems, and especially modeling the interactions that the buildings have with the district thermal systems when you get to these 4th and 5th generation systems where temperature loops can for example, float during certain times of the year. This is just showing that they're really building kind of flexibility and these capabilities to model a range of different generations of district thermal systems, a range of different types of inputs from the building side, whether it's the actual modeling of the specific buildings with SPAN, or it's taking time series data measured from buildings, or using reduced order model of the buildings, and then integrating those in with the model of the district thermal system. So there's more in these last sets of slides than we could probably do a whole nother presentation on these capabilities. These are all ongoing activities, and our idea is developing out these integrations with other types of tools so that commercial developers can then leverage these and to be able to do this sort of multi-discipline, multi-technology type of modeling. And that again is kind of going back to the core approach of URBANopt, which is taking a modular open source approach to help manage data exchange and integrations with a variety of tools. So next slide. Just wanted to end by acknowledging that the work we've covered today represents many contributions from a variety of teams. Specifically, folks that I haven't mentioned, we're working with Skidmore, Owens, and Merrill, to working with Ladybug Tools and SOM to pilot these capabilities on real district projects and get feedback from architects and master planners to help drive the development of the tools. We're also working with Comillas University in Spain. They have a tool that can lay out optimal distribution system configurations. So look for more on that. And then we have some other partners in Colorado School of Mines, and I did mention NG as well, advising on some of the district thermal system modeling. Also just want to thank DOE for the support in terms of developing these capabilities. And then I think with that, we'll go to the end of our presentation. We have a few references here, and then we'll open it up for questions. So thank you, and look forward to the discussion with the time we have left.
All right. Thank you, Ben, Rawad, and Chris. This has been a very interesting presentation. I want to invite everyone who's attending to participate in a discussion now. You can type your questions into the chat window, and I've set the Zoom meeting so that if you have a microphone, you will be able to unmute yourself to ask your questions. While people are thinking about their questions, I just want, first of all, to remind everyone that AIA credit is available for this presentation. Please email your AIA membership number and your name to info@aiaeb.org. And then I'd like to start out by asking a question of my own. It's really impressive to see how, for someone who's already, a Ladybug or Honeybee user, this seems to be a very approachable tool for district or community energy modeling. But one of the daunting things about energy modeling at that scale has always been the amount of time it takes. So I'm curious, what timescales are we talking about? And I think, Chris, you mentioned that there's parallelism involved. Is that limited to your desktop? Do you have access to the cloud? How does that work for a user?
Yeah, great questions. Thank you, Nathaniel. So maybe I'll first start off by addressing the time question. So I mean, our kind of philosophy with Ladybug Tools, we borrowed from, I guess I'm quoting the founder of Atari when he said they try to make things easy to start but impossible to master. So we have really tried hard to make it easy to start so that you can set up these models. And you can, have all the properties assigned to them that would be needed to execute them. But I mean, of course, the reality is that the real world is complex. And chances are that you'll really need to get into some of the details if you're, let's say, calibrating a certain model you've built to a real urban district, or really trying to represent the actual, level of detail that may be necessary to model certain strategies. And so that's why we've tried to make it as flexible as possible, so that even if you can set up that model very easily, you can drill down all the way into those individual rooms and the individual properties of those rooms to edit them, and if need be, in order to essentially have the flexibility to model the real world complexity. And so yeah, so if that's what I can say about time, that it may still require some time, quite amount of time to actually get something to match to a real data set, but we don't want that time to be spent in, tedious tasks per se, that you should be able to set it up quickly and then delve down into what is needed. And maybe I'll just also say that we have even a Python SDK, so you're actually able to even to edit properties that aren't even exposed on the Grasshopper components. You can edit properties of the rooms that aren't that are really deep under the hood that you may not even normally need to edit for a typical model. So we've really tried to make it as flexible as possible. To address so that kind of addresses the question of setup time, model setup time. To discuss the question of simulation time. So maybe just to give a benchmark, that model of 30 buildings that were produced from building massings, downtown building massings, that took about an hour and a half to run on, I guess, granted, it's a very good desktop machine, but on my machine running things in parallel with 10 cores. So if that gives a sense, whereas it may have taken like a full day to run something like that on a single core, the parallelization is really, really key to making things work. At the moment, we're trying to work on also the ability to even export each story of a building to a separate model, so that if you wanted to, you could even parallelize it to run, let's say, 100 CPUs, and then run each story on an individual core, so that it would be even faster. We're in the process of working on that now. And we're also in the process, we have a cloud service, like our primary business model with Ladybug Tools is that we're producing a cloud service product called Pollination Cloud. And we're in the process now of working on specific workflows that will be able to execute these types of large scale urban models in reasonable project timeframes with access to, let's say, 100 CPUs with some of the prototypes we've done so far. So that's also a solution that we're working towards. But of course, as always, that cloud service is our business, but it's always, everything we produce here is free and open source, and it's always free to run everything locally.
All right, thank you. We have a question coming from Alberto. Alberto, would you like to unmute yourself and ask your question?
Sure, thanks, Nathaniel. Can you hear me?
Yes.
Okay. First of all, great presentation. I am really enjoying it, and congratulations on that. My question is, does URBANopt include some heat island effects for analysis of blocks or cities?
Chris, do you want to?
Yeah, I can take that one. Yeah, so we are, some of you, if you were familiar with the kind of legacy version that we had of Dragonfly, it was actually just a means of exporting urban geometry to an engine called the Urban Weather Generator. And that came out of MIT. It's open source, and its essential function is to morph EPW files from a rural or airport setting to account for the urban heat island effect. And we have a lot of the underlying infrastructure in Dragonfly set up now to simply take your Dragonfly model and export the necessary properties for the Urban Weather Generator. And we should be exposing that within, I think, by the next stable release of our Grasshopper plugin. It should definitely be there. And we'll be putting in the development version of the plugin within the next month or two. So yeah, so there's stuff in the works to be able to morph EPW files for urban heat islands, so that you can then look at the effect of that on the urban energy use and on even eventually outdoor thermal comfort and other metrics.
Thank you.
All right, thanks, Alberto. We have another question coming from Alex. Alex, would you like to ask yours?
Yes, thank you. My question is, well, I have two questions. One is, I'm not too familiar with the GeoJSON file format, and I wasn't sure like how you generate that. Is that something you can like make in SketchUp or something? For example, I had a recent project where I was doing something kind of similar, and I had some existing buildings and then some new buildings. So like new proposed design buildings. And then the second question is, with the video demo, it wasn't clear how, when you brought in the GeoJSON, you talked about applying the building heights, and you showed that, but I wasn't really clear like how to assign specific building heights to specific buildings. Like it just kind of looked like a group of buildings, but I wasn't really sure how you like distinguish which one you're assigning the building height to.
I don't know if we're water, but if you want to talk generally about GeoJSON first, and then I can answer some of the specific Dragonfly ones.
Go ahead, Rawat.
Yeah, so for URBANopt, this is not an end user interface. So what we now are supporting a GeoJSON format, but also like in the modules, we can also support other kind of formats, like for example, CCGML. But in order to do this, we have to develop a module that can take in this type of format. So the platform is flexible to integrate new modules, to integrate other formats of the geometry and geospatial information.
Yeah, so just into this diagram, I know Rawat is along what you referenced that there's a gem specifically for GeoJSON, but there are extensions in URBANopt that link out to that, you know, for different formats. And for those of you who are unfamiliar with GeoJSON, it's fundamentally a 2D representation of geospatial information. So it's all features are represented in terms of latitude, longitude coordinates. It's a human readable file format, but it's if you guys are familiar with shape files, they're similar to those GIS format. But essentially, I mean, to answer your question about how the floor heights are being assigned to the footprints I have in Rhino here. So these are Rhino geometries I have in this case that I've imported to Rhino Grasshopper from a using one of the other Grasshopper plugins that's available. There are lots of geospatial plugins available. But you can see what's happening is that in this case, I'm simply plugging in a list of those footprint geometries, and I'm assigning the same sets of floor heights to all those. So there was a list of three values there, and each of those was a floor height. You see these three individual threes. So the first floor is at 3 meters, the second floor is at 3 meters, and the next one above that is at 3 meters. But you can change those, adjust those to be whatever floor heights. If the bottom story, let's say, is taller, you could say 4, 3, 3. Yeah, I mean, I don't want to get too much into the details, because if you download the interface, install the plugin, each of these components gives you a description of the inputs for it that will tell you exactly what you can input into them in order to be able to split up or basically turn your footprints or your building massings into individual stories.
Okay, thanks.
We have a question coming from Argyris. Argyris, would you like to ask yours?
Yeah, sure. Can you hear me?
Yes.
Yes.
Great work, guys. It's very exciting. The question is it in your plans to use measured data and calibrate and validate the model?
Yes, it is. We so you know, I think a lot of the discussion today was a little bit more focused on sort of a new construction maybe approach. We are very much focused as well on kind of workflows around existing communities, and recognize that, of course, if we want to make significant impacts, we have to think about how we can go in and upgrade buildings to be more energy efficient, integrate more renewables, and more. So some of the things that we're working on, we have in our piloting of these capabilities with SOM and Ladybug Tools, we're going to be working on piloting workflows around existing community analysis, and in particular, situations where you have kind of a mix of data, whether it's maybe some footprint data plus maybe some county assessor data. Maybe some of the buildings are big enough that you have public disclosure requirements around energy consumption, so you might know kind of annual energy consumption. But then the key question is what how do you get a good baseline model for those communities? So we're going to definitely be looking into calibration of and sort of benchmarking against measured data. And we do have maybe I can add it afterwards in the references, but we do have some prior publications where we've used URBANopt platform to analyze some existing communities. In particular, there's a community in the Huntington Beach area where we're basically piloting a lot of these capabilities through a CEC funded project to analyze potential upgrades to those communities, or to that community, I should say. I think just to wrap that up, just recognize that one of the key differences is, from an individual building scale, is that you could have calibration at various levels, whether it's, you have data on individual buildings, maybe you have data at a transformer that could have multiple buildings on it, or even up to like a substation level type, or feeder level. So good question.
All right, thanks. I see we have one more question that's come in. This is from Neslihan. Neslihan, are you there?
Hi.
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 Can you hear me?
Yes.
I'm from Turkey. It was a very great presentation. Thank you very much. I'm wondering if it is possible to model the district with a complex topography.
In terms of like street layout, or you're talking about elevation?
Elevations, for example, topography can change slopes of the places. How can I define differently? Not a flat surface. Topography can change.
Chris, do you want to talk about
Sure,
that one?
yeah. I mean, that's perfectly acceptable to have buildings at different elevations. I mean, at the end of the day, everything gets converted to that 3D format. So, those differences in elevation will make it into the urban model. Yeah, I realize though, yeah, because we use the GeoJSON, which is a 2D format, and a lot of the examples I showed were flat ground. That's not a limitation. You can model any different elevation changes between those building massings or footprints.
Okay, thank you.
Yeah.
I see a hand up in the audience. This is from Mao Mao. Would you like to ask yours?
Yes. Can you hear me?
Yes.
Yes. Thanks for the presentation and very illuminating software. And my question is, imagine that if we have like 100 like buildings, and I want to know how you can collect the parameters of the building envelopes, the occupancy profiles, and the system parameters. Because currently I'm in the UK, right? And my research topic is quite like investigating like a residential community, and there are might be around like 1,000 households. And the challenging thing for me currently is how I can collect all of the occupancy profiles and the building envelopes to input a model. So I think your software is quite useful, but I mean, how can I like collect these parameters? Do you have any like suggestions? Thanks.
Do you mind if I just ask to clarify? Do you mean like measuring out in the real world, or just how would you assign those to a model that you're building?
I mean, how do you yeah, the real world, how you collect the data and input them to your model? Thanks.
Yeah, so that's a key challenge, and I think so. So much of for existing communities, so much of the data collection challenge or strategy, maybe is a better word, depends on the specific questions that you're hoping to answer with the modeling, right? So if you're for example, in your modeling wanting to be able to accurately predict the energy savings of any upgrades to individual buildings with that community, then it's going to become much more important to collect accurate information about those individual buildings. Whereas if you're asking questions that maybe are at a more aggregated level, then it might not be as critical to get any individual building exactly right, but it might be really important that on average you're getting the range of characteristics correct or generally correct. One thing that I might suggest is taking a look. There's another open source software platform called ResStock that is also developed NREL is also contributing and leading the development of that platform. That takes more of a statistical approach for characterizing the existing housing stock. In this case, it's in the United States, but I imagine the approach could be translated to other countries as well. So there, it basically mashes together a bunch of different data sources to come up with probability distributions for different housing stock characteristics, and then uses those distributions to kind of sample and create archetypes for different houses. So maybe something like that. If you're kind of more interested in like aggregated questions, but ultimately if you're going to be trying to predict savings or the impacts at an individual building scale, then you're talking about some type of energy or efficiency assessment for the individual homes, I think, or maybe it's a remote type of energy audit or something.
And maybe I'll just add that if you are starting from no information at all except for, let's say, the geometry, the building program, and the year when things are built, you can at least construct something using the templates, the ASHRAE 90.1 or ICC templates that are included with the plugin, so that you can at least, I mean, granted, that's a very coarse start where you're just starting from a best guess, and then as the things that Ben mentioned, as you get more information from assessments or surveys or other data sets, you can refine that and make that more accurate to what you need.
Okay, thanks for your answer. Another quite silly question. What is the difference between like the community and the district?
So good question. I know they're both
yeah, quite confusing.
Used interchangeably, I think, to some extent. I do think often districts have a little bit more of a commercial building or industrial connotation, whereas communities, I think, tend to have a little bit broader range to also include, for example, neighborhoods. Yeah.
Thanks.
All right. I see we have a hand up from Azin. Azin, do you want to ask your question?
Hi, yes, thank you. So I have a question about the calculation method. I'm wondering to know that if shadowing studies of the neighborhood and other buildings is considered on energy calculation in this software?
Yes, yeah, because I guess there are always options with Energy Plus to turn it off, or to make it very simple. And there are options with Dragonfly if you don't want to count the surrounding buildings, because a lot of the calculation time of Energy Plus accounts for that. There are ways to turn it off, but by default, you're going to get the surrounding buildings in each model of the exported OSMs and IDFs as context shade, and so you will be accounting for that.
Okay, thank you. And for defining the archetypes and scenarios, is there what is the baseline for that? Is it based on the year, or can we define it by the, for example, height of the buildings, average height of the buildings, or different things? So because I never tried this software, so what is the default way of defining the scenarios and archetypes?
So I could say,
go
go ahead. You can say Rod. Yeah.
For defining the baseline, you usually select like a standard, like for example, ASHRAE standard to define a scenario, or other standards, for example, GEAR or ASHRAE. And this will and with this standard, it will apply all the standard measures to the buildings and map these standard simulation inputs and model them in a to create this baseline scenario. And how it works, it works based on OpenStudio measures. So for example, if you adjust the inputs of these measures and add the new measures that can apply higher efficiency levels, then you can start applying these in order to construct a different scenario outside of the baseline.
Okay, thank you so much.
All right, we have one last question that's coming. This is a clarification question. If you could explain how URBANopt connects to Medallica.
Good question. So I wonder if we still have Nick Long on. I'm not sure.
Ben or Rawad?
Can you hear me?
Yes.
Hello? Okay, I wasn't sure if, I think at one point we had Nick Long on who's leading that work. So essentially, when we're modeling district thermal systems, we're leveraging the Medallica language or modeling approach overall. So we're kind of moving from the Energy Plus OpenStudio modeling approach to a Medallica-based modeling approach. And there's basically a translator that that team has developed. So you can kind of start with your, using some of the workflows that like Chris was demonstrating and Rawad were demonstrating to generate a URBANopt GeoJSON file, and then there's this GeoJSON to Medallica translator that then translates those kind of features into a Medallica model for the district, and that translator is under active development, so we're kind of still pulling together capabilities there. But then once it's translated over, then you would be simulating the district thermal system, utilizing Medallica and Medallica solvers. And if you're actually modeling the individual buildings, then you'd be utilizing Spanum Energy Plus instead of traditional Energy Plus. Hopefully that helps answer your question.
And one more question is just coming to you. Is there any relationship between URBANopt and NVMet?
No, there's not a relationship.
Okay. All right. Well, thank you very much. This has been a great session. I know that we've run a little bit long, but we've had some excellent questions. I want to thank all of the speakers, Ben, Rawad, and Chris, and also thank everyone for attending. And especially I'd like to thank Bauman Consulting for sponsoring this. It's our sponsors who make it possible for us to continue to offer these webinars for free. Lastly, I'd like to remind everyone, please join us again on January 28th at noon Pacific time, when Kevin Vanden Windelenburg will present his research on reducing COVID-19 transmission in the built environment. Thank you, everyone.
Thank you.
Thanks.